All right, Advent of Code 2019, day 5 is called Sunny with a Chance of Asteroids. You're starting to sweat as the ship makes its way towards Mercury. The elf suggests that you get the air conditioner working by upgrading your ship computer to support the Thermal Environment Supervision Terminal. Test. Test starts by running a diagnostic program, your puzzle input. The test diagnostic program will run on your existing encode computer, okay, after a few modifications. First, you'll need 2 new instructions. Opcode 3 takes a single integer as input and saves it to the position given by its only parameter. For example, the instructions 3, 50 would take an input value and store it at address 50. Where does it get the input value from? Opcode 4 outputs the value of its only parameter. For example, the instruction 450 would output the value at address 50. Oh, okay, so it reads address 50 and outputs it, whatever that means. We don't know yet. Programs that use these instructions will come with documentation that explains what should be connected to the input and output. Okay. Scoop says, did you factor your encode into its own mod? Yes, it is. And I'll show that in a second, as soon as I'm done reading here. The program 304099 outputs whatever it gets as input. Second, you'll need to add support for parameter modes. Each parameter of an instruction is handled based on its parameter mode. Right now, your ship computer already understands parameter mode 0, position mode, which causes the parameter to be interpreted as a position. The parameter is 50, its value is the value stored at address 50 in memory. Until now, all parameters have been in position mode. Now your ship computer will also need to handle parameters in mode 1, immediate mode. In immediate mode, a parameter is interpreted as a value. The parameter is 50, the value is simply 50. Okay. All right. So yeah, we get all that. This is standard VM stuff, right? Parameter modes are stored in the same value as the instruction's opcode. The opcode is a 2-digit number based only on the 1s and 10s digit of the value. The rightmost 2 digits of the first value in the instruction. Parameter modes are single digits, 1 per parameter, read right to left from the opcode. The first parameter's mode is in the hundreds digit. Okay. And the second parameter's mode is in the thousands digit, and the third parameter's mode is in the 10,000 digits, and so on. Any missing modes are 0. For example, consider the program 1002-43433. The first instruction is a multiply instruction, right, because it's 0, 2, right? Then going right to left, parameter modes are 0, because it's not shown. Oh no, the hundreds digit, right. Right to left. Parameter modes 0, 1, and 0. Not present and therefore 0. Okay, so it's A, B, C. So C is the mode of the first parameter, B is the mode of the second parameter, and C is the mode of the third parameter. Okay. This instruction multiplies the first 2 parameters. The first parameter, 4 in position mode, works like it did before. Its value is the value stored at address 33. Okay, I think I get this. 3 is in immediate mode, simply has the value 3 because that's the instruction. We're multiplying. First parameter, 4 in position mode, works like it did before. Right. So this is the first parameter. It's in position mode, which means you read from address 4. This is immediate mode, so we're just reading the 3, and then 4 is also position 4. Okay. Parameters that an instruction writes to will never be in immediate mode. Yeah, that's why he defaulted to position mode in the first version. It's important to remember that the instruction pointer should increase by the number of values in the instruction after the instruction finishes, because the new instructions, this amount is no longer always 4, right? I'll have to fix that. Integers can be negative. Okay, no problem. The test diagnostic program will start by requesting from the user the ID of the system to test by running an input instruction. Provide it 1. The ID for the ship's air conditioner unit. It will then perform a series of diagnostic tests confirming that various parts of the encode computer, like parameter modes, function correctly. For each test, it will run an output instruction indicating how far the result of the test was from the expected value. where 0 means the test was successful. Non-zero outputs mean that a function is not working correctly. Check the instructions that were run before the output instruction to see which one failed. Oh, neat. Okay, so it kind of does a little testing for you. Finally, the program will output a diagnostic code and immediately halt. This final output isn't an error, and output immediately by a halt means the program finished. All outputs were 0 except for the diagnostic code. The diagnostic program ran successfully. After providing 1 to the only input instruction and passing all the tests, what diagnostic code does the program produce? Okay. So first, I think we're going to have to mess around with our intcode computer before we do anything else and just get that part working. We have opcode 3, which takes an input and saves it to the position given by its only parameter, which means a couple of things. We're going to need to extend the opcodes. And we're going to have to change this here. Right now, we're just incrementing by 4. We're going to have to extend the opcode here. We're also going to have a way of pushing data as input and then generating output. So I wonder if we can extend run to return a value of the most recent output, and it should stop every output. No. We want to be able to run it to completion, right? And then just grab all the outputs. Maybe the output should be stuck in a vec or vecdeck and queued up that way. Let's see. So if we have opcode, well, one thing we can do is have step return the number of instructions it read, right? And that way we can say let offset equals, and then this is offset. And then this just returns 4 here and 4 here. And this doesn't matter. We can just say 1 for now. The tests still pass. That's good. So what test do we have here? Yeah, so we have a bunch of tests for the encode, and those all still work. What we should do is create a test for input. So let's see. Program 304099 outputs whatever it gets it as input and then halt. Okay, so that would be a good test. Copies input to output. And we can just grab this. Okay. And then before we run it, we need to insert an input. So maybe we say computer push, let's say the number 123 as the input. We will create a push function. We'll run it, and then we should be able to say assert EQ 123 computer pop. Right? Maybe we use push and pop as our input and output functions. So this won't work because we don't have these functions yet. Can we add them? Generate the push method, generate the pop method. Oop, inline macro. No. Okay. So here's the push method. It doesn't return a value. But it is going to say on a mutable self, we're going to say self input push value, push back. And what we'll do is we'll have a couple of vecs here. We have the input queue, which is vec deck 64, output queue. All right, we'll just pull these guys in. And then output will be, oh no, yeah, that's right. That's right. So the input queue will push back, and then it'll pop front when we want to read the input. That makes sense. And then pop itself, and it returns an I6. Why did it pick I32 here? That's weird. What would be smarter is if I made this take a type, right? And then put the type in here, all the way down, rather than putting hard coding everything as I64. But I'm not smart, so I'm not going to do that. Pop is going to just say self output pop front. Like that. All right, and now what we can do is we can write opcode 3. Opcode 3. Oh yeah, we have to do we're going to have to modify everything for. That's fine. We'll for the addressing modes, but we can do that right up here. So this is just going to be we're going to read the input and put it in location 0, and then we're going to read the output and then return it. Read the output from position 0. No. What is would output the value at position? Read the value at position 0 and output it. Right. Okay. So let A equals self memory. We're going to just do this right now. Self IP plus 1 as usize. This is where we're going to store the input value. We'll say self pop front. Oh, input Q pop front. Unwrap, because it might. Yep, and then it'll blow up if there is no input. And it's going to store it now at location A. So self memory of A equals val. And we executed 2 values there. And then 4 is going to be similar. We're going to grab the memory location and push it onto the output queue. Let val equals self memory A. Self output queue push back val. And then we executed 2 instructions. All right. And oops. Input Q. Output Q. Oops. I put a 1 there. There we go. Unwrap. Okay. Look at that. So this test worked. Copies the input to the output. We're able to get that going. Do we have another test program? Okay, so yeah, we have the next test program which works on addressing modes. So I should be able to do that now. FN test addressing mode. Grab this. Put that there. And now this is going to multiply $99, and it's written to address 4. So we can just check to see the memory works right. So computer run, assert EQ 99 in computer memory 4. Right, and this should fail because we don't have instruction 1002. So this is where we're going to get our addressing modes. Let's see, let mode A is inst divided by 100 mod 10, and then B and C are going to be mod 1000 and 10,000, right? And then the actual instruction inst mod 100. So now we should get the modes, but we'll get the wrong answer. Instruction 32 at IP4 is unimplemented. What did it try doing? It should have done the multiplication. Oh, yeah. So it probably just stored it in the wrong spot. That's all. So we have to figure out how to do, yeah, it must have overwritten. I wonder if I can also print out all the instruction. That would be a little painful because, well, let's try this. Get input 2019 day 5. Yeah. I mean, it'll be a little painful to look at, but it'll give us the full diagnostic. And then we can just print memory this way. Self memory. Yeah, so put 132 there instead of 99. Because we multiplied the wrong, we multiplied the address 3. Wait, how's that work? Because we're doing everything in position mode. So it should be whatever's at address 4. Oh, yeah, whatever's at address 4, which is 33. And then we multiplied it by 3. Whatever was at address 3, which is 4. That's where the 32 came from, because it's 132. Okay, so let's figure out the addressing modes. Now, here's the thing is I don't want to have to mess around with these, right? In everything here, right? I don't want to have to say, like let's just do the multiplication one for now. I would have to say if mode A equals 0, then this, else, oh, no, down here, right? Whether or not we read A or B. Okay, so let val1 equals if mode A equals 0. This is painful. Then it's self memory A, else it's just A. And then we do the same thing for val2, except B and B. And then this would be val1 times val2. I think we can be smarter about it. Oh, A as I64. So we have to flip, yeah, so and we have to flip it around. It still didn't work though. I already casted 2 U size. Can they be negative? They can be negative, right? So this is all very, very bad, right? It would be better for me to have a get value, or maybe what I can do is I can model the memory instead of just having a vec of I64. Because there's probably going to be other addressing modes. I don't know if there's position mode, which is just, read from address. There's immediate mode, but then there's probably also, there might be others. Oh, Val is just using mode A. Thank you. That's why it's broken. Yeah. Okay, so now it's working. So this gets this working, but I don't want to have to write this code in every single instruction, right? Because we'll need it here as well. Yeah, and so this would have to be self. Now here's the thing, right? There's only these 4 instructions, so I could just do this. For now, and then refactor later. I do want to change this though, because this would be self memory, self IP plus 1 plus 2. You see how painful this is. And now it wraps. Yeah, see, I don't want to do this, right? Which is why I want to write something that can just give me, if I pass it in this thing here, it should tell me the value. See, that's the thing. It's okay. Let's write a little read instruction. Read self, and it returns an I64, and it's going to get an address to read from, which is going to be usize, and a mode, which is right now, I think these are all I64s. Yeah, but we can change that. We should make it a type. And we can say if mode equals 0, then we're going to just read from that memory address and return that. Self memory, let location equals self memory of address, and we're going to as usize, and we're going to return the self memory location. Else, if mode equals 1, yeah, I got to make this a proper thing. Self memory address, right? And then we can say, instead of doing this business here, we can say let A equal read this address, comma, mode A. And this read self IP plus 2, sorry, as mode in mode B. And then the destination is always going to be this way. So then it's A plus B. So let's see if that works. Oh, self read. Oh, and then this should be a panic. Bad mode. Some of the other users also have VMs. Yeah, that's true. Need a helper function that takes a memory location and mode. Yeah. Yeah, it would be nice to have like a memory model that I could just go to for that. Just now, how did you check the type of variable? Oh, yeah, let me show you that while I fix this up. If I just, right now I've got Rust Analyzer running in the background. If I hit Shift K, it pops up little information about what I'm hovering over. So I can hit Shift K on the read and it'll show me my read function and it shows where it comes from. All right, so that still works. I think this makes it a little cleaner, right? We can do the same thing here, self read, self IP plus 1, mode A. And then I want to change these. And this is A times B, right? And then this becomes the same thing here, self read, self IP plus 1, mode A. I guess mode C is never used. Now, there might be instructions that are longer. We'll hold off on that. I don't need to add it yet. So let's do that first. That's better. Okay. And then here, this last one, self read mode A. Like that. Yeah, I think that's it. Oh, thanks, Scoops. Oh no. This is the input thing. So we actually need to store it at a location. Okay. This is where we're storing it. It's on line 38. Oh, here. Oh, this is always the memory location. Oh, yeah. This is always a memory location. The mode, I guess, must be ignored. Oh, no. This is mode 0. That's right. I got something wrong here. It doesn't need to call the helper because it's always going to be, I'm just reading what Scoops wrote. Memory. It's always going to be the address, but it should work. Oh no, because it's okay. You're right. You're right. I guess we ignore that part. Um, Saves it to the position given by its only parameter. Okay. Well, interesting. Anyway, so let's see what happens here. I should assert my modes for the desk value as a 0. I could do that. Actually, what I should, for now, the other thing I want to do is change these modes up. So we're going to make an addressing mode, which is going to be position. I don't like position, but okay, immediate. This is 0, 0, and 1, right? And we should be able to say impl from I64 for addressing mode. And it should be match value 0 self position, and 1 is self immediate, and anything else is panic invalid addressing mode value. Right, and then up here, I should be able to say into like that. There we go. And then this takes an addressing mode. I have to implement copy on it. And that blows up. So now we can say match mode. Right? And that way we don't have to have a panic in there. Addressing mode position. Addressing mode immediate. Oh, I misspelled it. And gotta close the mode. Okay, it's a little messy, but there we go. Okay, that's a little bit, I like that better. Boom, boom, boom. And then, yeah, I think, let's implement a scoop suggestion. We do this, and then assert here. That way we know we didn't break our computer. And for this guy as well, except this is mode A. This should be reading from a position, yeah. So it should also be mode A. Okay. Blam. Oh, I have to implement partial EQ. Yeah. Oh, we want debug on it as well? I guess we need that for the panic message. Did it say output was always from a position? Yeah, I think it did. Output's the value of its only parameter. Oh no, it doesn't have to be. This says it's position given by its only parameter, but this is saying output, so we could output immediate mode stuff. Okay, good call. All right, so are we ready now to implement, not there. Oh, we don't have it yet. So let's do this, get status. git add source intcode, git commit -m, upgraded intcode computer to handle input output and the immediate addressing mode. All right, and now we're going to say git add source, git commit -m prep for day 5. All right. Oh, oops. So here's day 5. So now what we need to do is take the input, which we already have. I already got the input. And now, oh, maybe we should run some more tests. It's a valid program. Find 100 plus -1 and store the result in position 4. We should make sure we can handle that, right? We did this test. Well, let's, you know what? Let's just be brave and run everything. I think we can handle negative numbers. I don't think that's a problem. We do want to read the input and grab and make the computer out of it. Let lines equals, I think it's a single line, right? Yeah, it's a single line. So we're just going to read AOC lib, read lines, input day 05, no, 2019-05.text. And then this is just a vec of strings. And we create our new computer. And then just say self computer equals int code new lines 0. I think we can do that. We have to pull in encode. Okay. And all we're going to do is run it, right? Oh, no, we have to run it and then get all the outputs. We do need to input a 1 before we run it. So that's what we're going to do here. I'm going to say self computer push 1. And then we'll say self computer run. And then it's going to stop, hopefully getting all zeros, but we'll find out. And then we have to output the last while let sum num equals self computer pop. I'm just going to print them for now and see what they all look like. Oh, push is private. Let's fix that. Oh. Oh. We should make pop return none if there isn't any. Okay, let's do that. Simplifies the code, doesn't it? Oh, yeah, and then I have to fix that one. Okay, let's fix that. Like this. Okay. Let's run it. I'm going to run it outside of Bacon, cargo run, just in case. Okay, so it did return a bunch of zeros and then the final number. So what do we want to do there? I guess what we can do is we can, what's an easy way to handle this? Should I have run stop on every output? And then we can check to see if the output is 0. The only thing is that, if it runs and it gives you a number and halts immediately, maybe if I create a run until output. And then it could just return that output. self running equals true, while self running let offset equals self step, self IP plus equals offset. If not self output queue is empty, then we're going to say return self output queue pop front. Otherwise, we're going to return none. Because it halted. Oh yeah, that's simpler, Scoops. Thank you. And then we'll flip over here and we'll say run until output. And then make sure it's 0 unless the program halted. No, it says that still doesn't help. That still doesn't help because we want to say, let some val, say while, is run until output. If val is not equal to 0, then assert. Yeah, maybe we could do this. Assert equals self computer run until output dot is none. And then we'll say return AOC lib output val. And panic. No solution found. Will that work? With an equal sign in there? We're not using pop yet. That's okay. But it does give us the number we're looking for. Let's flip back to encode and remove the pop function for now. We can always add it back. It's not hard to implement. All right, let's see if this is the answer. Submit. Hey, that's the right answer. Okay. I'm happy. So git diff. So this is all of our encode stuff, but we also modified this to handle the run until output. Oh, this test is going to fail now. Oops. Okay, so what we can do is just make it a test function. Or I should be testing the run until assert equal run until output, right? There we go. And I should also assert that the next one is none. Yes, perfect. And then assert that computer running, is running? Yeah, it's just running. Why isn't the running completing? Right, it should be halted. Okay, good. Git add source encode, git diff staged. You set running to false when you return none. Ah, good question. Yeah, it's going to be coming out of here because we set running to false in the halt instruction. Yeah, so it should be false. And that test does pass. So git show diff staged. What happens when you run until output twice after a none? I think it'll blow up. The same thing it would happen if I called run and then run immediately afterwards without doing a reset. Yeah. But I like the way you think. You're always thinking about, you know, what could go wrong and come up with those kind of questions. That really helps. Git commit -m, add a run until output function instead of using pop. All right. And then git commit -am 2019 day 5 part 1. You're good at finding what could go wrong generally unexpectedly. That's good. All right, let's go on to part 2. Continue to part 2. The air conditioner comes online. Its cold air feels good for a while, but the test alarms start to go off. Since the air conditioner can't vent its heat anywhere but back into the spacecraft, it's actually making the air inside the ship warmer. Nice. Instead, you'll need to use the test to extend the thermal radiators. Spacecraft thermal control. Fortunately, the diagnostic program, your puzzle input, is already equipped for this. Unfortunately, your encode computer is not. Oh, okay. So we're going to add 4 more instructions. Jump if true. The first parameter is non-zero. It sets the instruction pointer to the value from the second parameter. Otherwise, it does nothing. Jump if false. If the first parameter is 0, it sets the instruction pointer to the value from the second parameter. Otherwise, it does nothing. Opcode 7 is less than. If the first parameter is less than the second parameter, it stores a 1 in the position given by the third parameter. Otherwise, it stores a 0. And opcode 8. Okay. So we have some tests. Let's use some tests here. And we're going to upgrade our int code. I'm going to move this addressing stuff to the top so that we can have our tests at the bottom. There we go. So this is going to be using position mode. Consider whether the input is equal to 8. I'll put 1 if it is, or 0 if it is not. Let's see. So if we say test against 8, let's call it that, right? And we should be able to say let mut computer equals int code new this, right? And I should be able to run it 3 times. Give it an input equal to 8. Oh no, it's just is it equal to 8, right? I was thinking of the case where it would be less than or equal to. We don't have that. Okay, so we'll do this. It's using position mode. All right, so we're going to just test to see if the input is equal to 8. So we're going to say computer push 8, assert EQ. It is equal to 8, so we're going to have it return some 1, and then computer run until output. And then we're going to say computer reset, computer push 9. And we're going to have it assert some 0. All right, and this should fail because we don't have the instruction 8. So let's implement instruction 8. Oh, instruction 8 is equals. Okay. So we're going to say if the first parameter is equal to the second parameter. So we're going to say let A equals self read, self IP plus 1, mode A. Let B equals self read, self IP plus 2, mode B. And then we're going to push, we're going to say assert EQ that addressing mode position for mode C. And then we're going to say yeah. So I'll just steal the, oops. I'll just steal, I was going to say, steal these lines. 28J, put these here. A equals B. That's I64. And this is a 4-byte instruction. Okay, so that test passes. I'm ignoring the jumping right now. This checks to see if the input is less than 8. Scoop says if you change 99 to return a 0, it'll always execute the halt instruction after you run again. If we leave the instruction pointer on the 99. So then next time you call run, because it'll set running to true, it'll execute the halt again and return 0. Yeah. If we need to do that, well, I should change this to 0 then, right? If we need to do that, I will do that. All right. So let's call this test equals 8. And we're going to change this to test less than 8. Right? So the new instruction is 7 that we're going to be executing here. So is 8 less than 8? No. Is 9 less than 8? No. But 7 is less than 8. Computer reset. 7 and 1. Okay, so that should blow up. That we haven't implemented instruction 7, but instruction 7 is almost the same as instruction 8. Oops. So we can just grab this. I should actually make this an instruction type. So we can match it instead of against numbers. We actually match it against instructions. But that's okay. So we just change this to less than. So it's exactly the same. Yeah, and that test passes. Okay. So now we've done that. And we can test it using immediate mode. I trust my code. Here's jump tests. Jump tests to take an input and output 0 if the input was 0 or 1 if the input was non-zero. Okay. So let's implement the jump test. Let's use immediate mode for the jump test, since I use position mode for the others. FN test jump mode. Jumps can return 0 if you need to jump. I was hoping to be cleverer about that and actually calculate the new address offset and jump there. Maybe that's dumb, but we'll see. Not necessarily cleverer. I shouldn't have said that. Take a different approach. So if we're going to say computer push 0, assert EQ, sum, output 0 if the input is 0. So 0, computer run until output. And I say computer reset, computer push 123, and it should be equal to 1. And that's failing because, oh, because I didn't put the right test in there. Yeah, copy that, paste it here, and now it should tell me, yeah, so instruction 5 is not implemented. Okay, let's do that. So this is what I'm thinking, is that because we're returning our offset, instead of changing it, doing a use size, we're just adding an offset to it. Now, what's the tricky thing here is changing this to an I64, it might complain. Yeah. Can't add assign I64 to usize. Maybe what we have is instead. Yeah, I don't want to play around with magic numbers, but what we can do is have an enum for this. What should we call it? Next PC, next IP. We can have an add 4, add 2, a jump 2, usize, and then just do it that way. A wrapping add should work. All right, we can try it that way. We'll do that here as well. Right? And then change this again to an I64. Will that build? Now it's still asking for that. You can convert an I64 to usize and panic. Oh, this returns the new value. Okay. But it's still complaining, right? Because I don't want to convert this into a usize. Oh, offset as usize? Well, what if I return a negative offset? That's the reason I'm switching to an I64, is I want to return a negative offset if I'm jumping backwards in memory. You think that would work? Is if I just say as usize and it wraps it around? Yeah, no, I know how 2's complement works. But let's try it. Oops. Yeah. Okay, so here's our jump instruction. So instruction 5 is jump if true. If the first parameter is non-zero, it sets the instruction pointer to the value from the second parameter. Otherwise, it does nothing. All right, so this is where we have to do our fancy math. So we're going to do these guys here. And then we're going to say if the first parameter is non-zero, if a is not equal to 0, then we're going to do this. Otherwise, we're going to return 2. Right? It does nothing. So b is where we want the instruction pointer to be. So it'd be self IP, no, b minus self IP as I64. And then we don't have instruction 9. Oh, wait. That means we did the wrong calculation here. Because you're saying up here, this is self IP plus the offset. Oh wait, let's take a look at what the actual initial memory was. Yeah, 331105 and -1. So this is instruction 5, and we're reading from negative. We're comparing 1 and 5 actually. It should be 3, right? Yeah, we figured it out at the same time. Okay. Oh, good. So that was the right calculation. All right, and now the only other one is number 6, right? This one also has 5. There's no 6s here. And here's a larger example. Do we have a 6 in here? I don't see a 6 in here. The above example program uses the input instruction to ask for a single number. The program will output 999 if the input value is below 8, 1,000 if the input is equal to 8, or 1,001 if the input is greater than 8. Okay, test 3-way for 8. Let computer equals int code new. And I bet you there's going to be a 6. There's going to be a 6 in the actual input that we're going to be running. So we'll see. Oh, you see a 1006? Oh yeah, there it is. I see it. Okay, good. So now we're gonna try it 3 ways, right? We're gonna say computer push 3, assert EQ sum 999, computer run until output, and computer push reset, computer push 8, and it should be equal to 1000. And then we're going to push 123, and it should be 1001, right? Yeah, 1001. Okay. So now this should not work because we don't have 6 implemented. Result unwrap on error value. Oops. Oh, do I have a space in here? I bet you I have a space in here. Yeah. That's it. Okay. Yeah, instruction 6. Okay, good. So instruction 6 is going to be just like this, except jump if false. If the first parameter is 0, it sets the instruction point. Okay. What's going on here? There. There. Okay, now all the tests pass. So let's commit, oops. Let's commit these changes. Yeah, okay, so we added the 4 new instructions. Git commit -am, added test and jump instructions. Good. 2019-5. All right, so I think we're now ready to do whatever part 2 is going to ask of us. Oh, it's just basically provided 5. Okay. And then we're going to get the same diagnostic code. So it's the same code, except we're pushing 5. So we're going to say fun run computer with val i64, i64. Right? And then we do that, and then we just say return val. We can still do a panic here. And then this just becomes AOC lib output run computer with 1. And this is run computer with 5. Let's run this really quickly. So it's 977 50 37. Oh. Bummer. Okay, so yeah, we could just make it a self. Impl AOC 2019-05. And then this becomes self dot. Oh, because I put a semicolon there. This val is not used. That's, thank you. Thank you, thank you. And this panic with no solution found. Oh, because I didn't do a reset. There we go. We got a different number. Hey, that's the right answer. Look at that. Okay, git status. So it's just that diff. Scoop says pretty. Yep, I agree. Git commit -am 2019 day 5 part 2. All right.